People love and hate paradoxes. Paradoxes are places of confusion, of conflicting ideas. They pinpoint the stickiest parts of our knowledge and understanding. They are often used as a testing ground for our scientific and mathematical assumptions and methods. But our reactions to different paradoxes vary wildly. Some feel truly perplexing, while others are just annoying. So here are 24 paradoxes ranked from least to most paradoxical by my former 12-year-old students. They, and everyone, have their individual backgrounds and perspectives which inform their reactions to paradoxes. I think that's pretty cool. So please feel free to politely disagree. First off, what is a paradox? A statement claiming something which goes beyond or even against common opinion, what is usually believed or held. One, such as a person, situation, or action having seemingly contradictory qualities or phases. Any conclusion that at first sounds absurd, but that has an argument to sustain it. The 24 paradoxes on this list were selected using a very simple criterion. They are commonly called paradoxes. I have loosely and very informally lumped them into categories. We don't have time to go into the details of all the paradoxes. That would be a very, very, very long video, but don't worry, I have left plenty of links in the description. Many of the paradoxes at the bottom of my students' list are what the philosopher Quine called veridical paradoxes. The word comes from Latin and means truthful. These paradoxes are surprising or counterintuitive, but they are true in the sense that they follow from some accepted mathematics or logic. One famous example is the birthday paradox. The more people you have in a room, the more likely it is that two of those people share a birthday. How many people do you need to have in a room before there is at least a 50% chance that two of them share a birthday? Most people guess a pretty big number, since there are 365 or 366 days in a year. But it's 23. Once you have 23 people in a room, there is at least a 50% chance that two of them share a birthday. And you can figure this out using math taught in an Introduction to Probability course. Also using introductory probability, you could solve Bertrand's box. You have 3 boxes, one with 2 gold coins, one with 2 silver coins, and one with a gold and a silver coin. You randomly pick a coin without knowing what box it came from. You look and the coin is gold. What is the probability that the other coin in the same box is gold? Most people say 1/2. Here's their logic. You're equally likely to have pulled from the first or the third box. The first box gives you a gold coin and the third box gives you a silver coin. But this logic is flawed. You are not equally likely to have pulled from the first or the third box. There are 2 gold coins in the first box and only 1 in the third. So if you pick a coin and see that it was gold, there's actually a 2/3 chance that it came from the first box. Therefore, there is a 2/3 chance that the other coin is also gold. This did not impress my students, and they put it at the bottom of the ranking. They were slightly more impressed with the similar and much more famous Monty Hall problem. That's the one with the doors and the goats and the car. I'll leave the details in the links in the description. These 3 paradoxes all point to the fact that calculating probabilities can be counterintuitive. It's a problem in statistics and applied sciences where computing the likelihood of certain outcomes, where a hurricane will make landfall or whether a patient has cancer, can have life or death consequences. Speaking of scientific predictions, my students were not moved by the Fermi paradox. That's the one about aliens. The reasoning goes, there's a boatload of stuff out there, stars that are similar to our sun and planets that are similar to our Earth. There are so many planets that it's very, very likely one of them would have developed intelligent life and we would have some kind of contact with these aliens. But of course, that hasn't happened. That's the paradox, the seeming contradiction. The Fermi paradox is like many of the other paradoxes in this section, which is roughly about philosophy and science. These paradoxes tend to have a lot of context. They're part of a long background conversation, which can be harder to summarize than a few mathematical axioms. That background perspective, those assumptions, are critical to how we react to the paradoxes. For example, you may not have spent a lot of time considering the word heap, that's a synonym for pile, as in a heap of sand, but some philosophers have. What makes a heap? If you have 1 grain of sand, that's not a heap. Adding a single grain of sand is not going to change that, so 2 grains of sand is also not a heap. But if 2 grains of sand is not a heap, then adding 1 more won't change it, so 3 grains of sand is not a heap, and so on. It follows that any number of grains of sand is not a heap. That's the paradox of the heap. It hinges on the vagueness of the word heap and our intuition that a single grain of sand can't change something from non-heap to heap. But then, how does it ever become a heap? You can contemplate the definition of heap the next time you're sitting in traffic, which is the subject of our next paradox. Let's say there are 2 different routes connecting downtown to the suburbs. In the afternoon, lots and lots of people are driving from downtown to the suburbs, so we'll only consider traffic flowing in that direction. Let's say there are 2,000 total cars. Some parts of the route take a specific amount of time. For example, it's 30 minutes to drive from here to here. But on other segments, the travel time is a function of the number of drivers. For example, the number of minutes to get from here to here could be 5 plus the number of drivers on that segment divided by 100. The more drivers, the slower the traffic. Each driver takes the route that is best for them individually. They're not planning collectively. Half the drivers will end up going one way and half will go the other way. No one wants to switch because the other route would take them longer. So, doing the arithmetic, everyone has a 45-minute commute. The city wants to decrease the commute time, so they add a bridge at the midpoint. Drivers can switch which route they are taking if they want, which would hopefully improve the traffic situation. But on average, drivers spend more time getting home. That's Brace's paradox. Counterintuitively, the extra road can cause extra traffic. In our example, the drivers will all end up changing to the same route. First the lower path, then the bridge, then the upper path. That makes the commute 50 minutes, 5 minutes longer than before. Remember, each driver is calculating the best route individually, and each driver has no incentive to switch routes. The other routes would take longer. But of course, if everyone collectively agreed to stop using the bridge, they'd all save 5 minutes. Our next paradox, or set of paradoxes, is particularly famous in the history of philosophy and mathematics, Zeno's paradoxes. They all have to do with motion and time and space and infinity. One of them is a funny version of the tortoise and the hare story. The hare can never catch up to the tortoise because by the time the hare reaches the tortoise's former position, the tortoise will have gone further, always keeping a tiny lead. That continues the whole race. Quine called this a falsidical paradox, as in false. In my experience, when people first encounter Zeno's paradoxes, there are several of them, they either love them or hate them, and my students kind of loved them. Almost as much as they loved the ship of Theseus. Theseus, a character in Greek mythology, had a ship. As the wooden planks rotted and decayed, he replaced them with new ones. At some point, every plank had been replaced. Is it still the ship of Theseus? It sort of feels like yes and no. That's the paradox. The story is used to discuss identity, what makes an object the same object throughout time, and composition, how is an object related to its constituent parts. Next up, the omnipotence paradox. It's about an omnipotent being. Omnipotent meaning all-powerful. In the best-known form, the paradox asks, can an omnipotent being create a stone so heavy that it cannot lift it? Omnipotence implies that the being has the power to create any stone, but it also implies that the being has the ability to lift any stone, hence the paradox. Earlier, I mentioned 3 veridical paradoxes. Those were all about probability, but they don't have to be. For example, I recently made a short video about the potato paradox, which uses basic algebra to produce a counterintuitive answer. My students were not impressed. They much preferred 1 equals 0.99999 repeating. In my experience, people have one of two reactions to this. The first reaction from people who have never seen this before is confusion or disbelief. There are lots of precise proofs of this fact, but here's a simple argument. Starting from the fact that 1/3 equals 0.3 repeating, we can add 1/3 plus 1/3 plus 1/3. This is obviously 1, and 0.3 repeating plus 0.3 repeating plus 0.3 repeating is 0.9 repeating. Therefore, 1 equals 0.99999 repeating. The second common reaction from people who have already learnt this fact is annoyance. This is everyone yelling at the screen, "That's not a paradox, it's a fact." Yes, many paradoxes are things we call facts. Those are the veridical paradoxes, which, as Quine writes, we can get used to, thereby gradually sapping its quality of paradox. You may be used to the fact that 1 equals 0.999 repeating, but for many people, at least at some point in their math education, this seems counterintuitive, surprising, paradoxical. Moving on, let's say you're getting married and want a very tall wedding cake. Each layer should be 1 meter tall, which is ridiculously tall. The bottom layer also has a radius of 1 meter. Then each subsequent layer narrows. The second layer has a radius of 1/2 of a meter. The third layer has a radius of 1/3 of a meter. The nth layer has a radius of 1/n of a meter. You tell the baker, "I would like infinitely many layers, please." The baker replies, "I don't have infinitely much cake batter." But you do a quick calculation. The volume of the nth layer is the radius squared times pi times the height. That's 1/n squared times pi times 1. Adding up all the layers, you get a famous infinite series, which Euler proved is equal to exactly pi squared over 6. Multiplying by the pi in front, the volume of this infinitely tall cake, known as Gabriel's wedding cake, is pi cubed over 6 cubic meters. That's a little more than 5 cubic meters. That's not that big. The Guinness World Record for the largest wedding cake is roughly 15,000 pounds or 6,800 kilos. I don't know what the volume of that cake was, but my guess is that it is bigger than Gabriel's wedding cake. The wedding cake paradox was resolved using a famous infinite series, and in general, infinite series can be quite tricky. Consider, for example, the sum 1 minus 1 plus 1 minus 1 plus 1 minus 1 plus 1 alternating forever. We can put parentheses like this, and then the answer seems like it's 0. If we put parentheses like this, then it seems like the answer should be 1. Maybe we should just average those answers and get 1/2, which is an answer with several other historical prominent arguments. But if your calculus teacher asks you the answer, it's none of the above. It's a divergent series, which kind of means that there's no answer. This is the consensus in modern mathematics following the standard rules for infinite series. Maybe if you've learned about those rules, these 3 different solutions don't seem very paradoxical, just wrong. But if you haven't learned those rules, or if you lived before those rules were invented or discovered or agreed upon, then it could be pretty perplexing that there are 3 different plausible answers to this summation. Thomson's lamp is, in some sense, a physical version of the alternating sum paradox. You're turning a light on and off instead of adding and subtracting 1. You enter a room and turn the light on. After 1 minute, you turn the light off. 30 seconds later, you turn it on. 15 seconds later, you turn it off again. 7.5 seconds later, you turn it back on. And so on and on, always having the time before you flip the switch. If you do this infinitely many times, it takes exactly 2 minutes. At that 2-minute mark, is the light on or off? That question is the paradox. It seems like it should have an answer. After all, lights are either on or off. But as you approach that 2-minute mark, you're turning it on and off arbitrarily quickly, and the status of the light at that 2-minute mark is very unclear. The Ross-Littlewood paradox is similar to Thomson's lamp. It's also something called a supertask, which means that you have to complete infinitely many tasks in a finite amount of time. But it's about quickly adding and removing balls from a vase. For the sake of time, I'm just going to direct you to an old Infinite Series video that I made about a random version of the Ross-Littlewood paradox. The St. Petersburg paradox is about a very peculiar casino game. The amount of money you win is determined by how long it takes to flip heads with a fair coin. If the first flip is heads, you win $2. If it's tails, then heads, you win $4. If it's twice tails, then heads, you win $8. To put it more mathy, if the first heads is on the nth flip, you win 2 to the n dollars. How much would you be willing to pay to play this game? Well, by some logic, you should be willing to spend what you will on average earn back. For example, if the average winnings in a particular lottery are $5 and the tickets cost less than $5, it makes sense to buy one. In the St. Petersburg game, how much do you expect to win? Just like our other probability paradoxes, you can use some rather simple calculations to determine that it's infinity. Your expected winnings are infinity dollars. So, given that, how much would you be willing to pay to play this game? Well, if you apply the same logic, paying anything less than the expected earning, you should be willing to pay any fixed price, say $10 million. The paradox is that even though the calculation tells you to pay whatever the fee is, most people are not willing to pay very much because usually on most turns, you don't win very much. It's not really a paradox in probability like the birthday paradox. It's more of a paradox in decision making. Self-referential paradoxes are popular. They're compelling and usually pretty easy to state. Here's the Berry paradox. The smallest positive integer not definable in under 60 letters. Lots of numbers can be defined in under 60 letters. 3, 112, but the alphabet is finite. It's only possible to define finitely many things in under 60 letters. Since there are infinitely many positive integers, they can't all be defined in under 60 letters. So, out of all of the positive integers which are not definable in under 60 letters, we'll call the smallest of that group x. In other words, x is the smallest positive integer not definable in under 60 letters. But that sentence has 57 letters, which means that it's a definition of x with less than 60 letters. That's the problem, the paradox. Another self-referential paradox, ranked slightly higher, is the Grelling-Nelson paradox. Autological words describe themselves. English is autological because it's an English word. Word is autological because it's a word. Heterological words do not describe themselves. German is heterological because it's not German. Truck is heterological because it's not a truck. Here's the paradox. Which category should we put the word heterological in? Is it autological or heterological? Well, if it's autological, then it describes itself. So the word heterological is heterological. But then if it's heterological, it doesn't describe itself. And that's the definition of heterological, so it fits its own definition, which makes it autological. Moving on. Here's a part of M.C. Escher's Ascending and Descending. The monk-like figures are marching on a never-ending staircase. You might say, that's an optical illusion, not a paradox. That's fine. It's not very high on my students' list. But paradoxes are an incongruity. They're a form of dissonance. When I look at this, I find it hard to resolve the clash between my intuition, the staircase is endless, with my knowledge that that's not possible. This is the Müller-Lyer illusion. Most people perceive the horizontal line on the bottom shape as longer than the horizontal line on the top shape, but they're the same length. What's cool about it is that different populations are more or less susceptible to the optical illusion. Visual artists, people with lots of experience drawing lines and considering perspective, are more likely to immediately recognize that the lines are the same length. Similarly, your background in mathematics or philosophy probably changes your reaction to the other paradoxes. Anyway, here's the pop quiz paradox. Your statistics teacher says that there will be a pop quiz next week. The class meets every day at noon. You want to figure out when the quiz will be so you can fake sick on that day. You think it can't be on Friday because then it wouldn't be a surprise. By Thursday afternoon, after class, when you still haven't taken the quiz, you would know it's on Friday, making it not an actual surprise. So then you cross off Friday. But then you reason it can't be on Thursday. By Wednesday afternoon, you would know that it's not on Thursday. You already know it's not on Friday, so a Thursday quiz would not be a surprise. Cross off Thursday. This pattern of logic repeats. A Wednesday quiz would not be a surprise. You would know by Tuesday afternoon, so no pop quiz on Wednesday. Similarly, no pop quiz on Tuesday or Monday. Great news, you figure. There's no quiz next week. But then, on Tuesday, your teacher gives you a pop quiz, which comes as quite a surprise. And that pop quiz is about Simpson's paradox. Let's say that Dude 1 has a higher batting average, that's a baseball thing, than Dude 2 in both 1995 and 1996. But when you combine the 2 years, Dude 2 has a higher batting average than Dude 1. Maybe that seems impossible, but it's totally possible. This is a simple, classic, and real example. But there are also lots of interesting modern examples that illustrate this statistical phenomenon. For example, this paper compared the COVID case fatality rate, that's the percentage of confirmed COVID patients who died, between Italy and China. Within every age group, this number is lower in Italy, but overall, it's lower in China. Within statistics, Simpson's paradox is not really an isolated phenomenon. Statistics provides many different perspectives on the same data, and they can often seem in conflict with each other. On to our most paradoxical paradoxes. Third from the top is the grandfather paradox. Briefly summarized, a kid goes back in time and kills her grandfather. But without the grandfather, the kid wouldn't have been born. And if the kid wasn't born, she wouldn't have killed her grandfather. But then she would have been born. But then she would have gone back in time to kill her grandfather, and so on and so on and so on. Physicists and philosophers use this and other time travel paradoxes to debate possible theories of time and time travel. Second from the top, we have the Banach-Tarski paradox. To be very brief about it, the Banach-Tarski paradox is a way to take a three-dimensional solid ball, break it into a few pieces, and reassemble those pieces to create two balls, each identical with the original. I'm not going to explain it here. It requires some time, and there's plenty of great explanations out there. But I want to point out a few things. First, it uses pretty standard, albeit advanced, mathematics. In that sense, it's a veridical paradox. But it also uses the axiom of choice. There are a bunch of foundational rules, axioms, in mathematics, and 100 years ago, these were heavily debated. In particular, this one, the axiom of choice, was quite controversial. One argument against the axiom of choice was that it led to some strange consequences, like the Banach-Tarski paradox. Now it's substantially less controversial. Paradoxes are all relative to the assumptions we make. Sometimes those assumptions are subconscious or otherwise difficult to identify. But in this case, the debate, the tension between the Banach-Tarski paradox and the axiom of choice is very clear. The number one top paradox was, unsurprisingly, the self-referential liar's paradox. This sentence is false. Is that true or false? Well, if it's false, then it's true, and if it's true, then it's false. It's classic, it's fun, it's a very good paradox. There you have it. 24 paradoxes ranked from least to most paradoxical by my 12-year-old students. I'm sure you have your own reaction to these paradoxes and many others, which is great. I think paradoxes are meant to be the start of a conversation. If there's a particular paradox that you'd like me to make another video about, please let me know in the comments. Here's just a quick note to say that I've started a Patreon. I've decided to make this video without sponsorship, and I hope to do the same going forward. These are my videos, free of the creative constraints and ethical questions that arise from commercial sponsorship. But I have to pay the bills somehow. So, if you have the resources, your Patreon membership would be greatly appreciated. Or if you'd like to support Chalk Talk in other ways, like subscribe, share with friends, write nice comments, everything helps. Thanks.